Educational Module, Machine Learning, Learning Unit, Advanced. Additional algorithms. Nearest neighbor methods are learning methods that work both on supervised and unsupervised tasks. The principle behind them is to find a predefined number of training samples closest in distance to the new point, and predict the label from these. The K-nearest neighbors algorithm KNN is a nearest neighbor method used for classification and regression. It relies on the principle that objects similar in the input space are also similar in the output space. It is a lazy learning approach since it does not have an explicit training process, but simply stores the training set instead. In the case of KNN, the number of samples can be a user-defined constant k, which should be large to minimize the probability of misclassifying x but also small, so that the points are close enough to x to give an accurate estimate of the true class of x. For every new element x, we define the k-nearest neighbors of x regardless of their class, and we assign x to the class with smallest number of samples p. It is effectively the majority vote of the nearest k-neighbors. As it is apparent, a distance metric, such as Euclidean distance, is required, which is presented in the following equation. This is the main algorithm for the k-nearest neighbors. Two example cases that illustrate the algorithm. The main positives are the following. It can yield excellent performance when used with a good distance measure. Also, it is robust to noisy data and outliers. The negatives are that, like all nearest neighbor classifiers, can be noisy if the data themselves are very noisy. Also, it has high computational cost. KNN classification. The output is a class membership. An object is classified by a plurality vote of its neighbors, with the object being assigned to the class most common among its k-nearest neighbors. KNN regression. The output is the property value for the object. This value is the average of the values of its k-nearest neighbors. Boltzmann machines can be seen as the stochastic counterpart of Hopfield networks and were one of the first neural networks capable of learning internal representations. They are named after the Boltzmann distribution, which is used in their sampling function. A Boltzmann machine is a model of pairwise interacting visible and hidden units that update their states over time in a probabilistic way depending on the states of the adjacent units and the associated energy. This energy is defined for the overall neural network. The restricted Boltzmann machine is a special type of a Boltzmann machine where the pair interactions are restricted to be between visible units and hidden units like a bipartite graph. This alternation of the architecture solves the problem of Boltzmann machines being impractical and having problems with learning, making them useful for practical problems. An RBM consists of two layers of neurons, the visible and hidden layer, while for training the contrastic divergence algorithm is employed. A deep neural network can be viewed as a composite of simple, unsupervised models such as restricted Boltzmann machines RBMs, where each RBM's hidden layer serves as the visible layer for the next RBM. As a result, Boltzmann machines can be used in a deep learning architecture, where each new layer that is added makes the model even better. An autoencoder neural network is an unsupervised neural network in which the target values are set to be equal to the inputs. Autoencoders are mainly composed of an encoder network, which transforms the input data, and a decoder network which reconstructs the data. At first, the autoencoder maps the input vector into a hidden representation by an encoder function. Then the representation is also mapped by a decoder function in order to be reconstructed. The training of the autoencoder involves minimizing the form of reconstruction and error loss. An autoencoder is able to learn nonlinear representations. An example of autoencoder: variations include the stacked denoising autoencoders, which have been proven to be an effective unsupervised feature extractor in different classification problems. The original idea is to insert noise and try to minimize the denoising reconstruction error. The hidden layer then is forced to discover more features instead of simply learning the identity